Hello, welcome to Fundamentals of Acoustics. Today is the third day of fourth week of this course. Starting this week, what we have been discussing is information about transmission line equations as they relate to one-dimensional propagation of acoustic waves. And in last two lectures, what we have covered is the transmission line equation related to pressure. And then we have used that equation to solve for the pressure field in an infinitely long one-dimensional tube, which is excited by a piston moving at its initial point. Now, in waves, you have not only pressure, but there is also a velocity wave equation, one-dimensional velocity wave equation. So, the transmission line equation for velocity and the transmission line equation for pressure, they are somehow interconnected. And what we will do today is to develop the relationship between the pressure wave function and the velocity wave function using some pressure velocity relationship. So, our aim is to develop the pressure velocity relations. So, pressure velocity relations. Now, in the last class or the class before that, we had developed this relation P of x and t equals real of P plus of s E minus s x over c plus P negative of s E s x over c, and this entire thing is in parenthesis multiplied by e to the power of s t. So, that is my first equation, and that corresponds to the transmission line equation for pressure. Now, if I consider the velocity wave equation, then I can develop a similar expression for velocity. So, u of x and t is equal to real of complex amplitude of the velocity wave moving in the positive x direction. So, I will call it capital U plus s E minus s x over c plus u minus s E s x over c multiplied by e to the power of s t. Okay. So, let us call this equation A1 and call this A2. So, I am getting equation A1 from the pressure wave equation, one dimensional equation for pressure waves, and I am getting equation E2 from one dimensional equation of velocity wave. Now, our aim is to find out how our P plus, P minus, U plus, U minus related. This is what we want to figure out. So, to figure that out, we go back to the momentum equation, and the momentum equation says partial of pressure with respect to x equals negative of density at STP conditions times partial of u with respect to time. So, that is my momentum equation. That is my momentum equation. So, I call this equation B. Okay. So, our aim is to figure out the interrelationship between u plus, u minus, p plus, and to figure that relationship we will use the momentum equation. So, what we do is we substitute substitute A1 in LHS and A2 in RHS of B, of equation B. So, when we do that, we get the following relation: real of. So, I have to differentiate equation A1 with respect to x in a partial way. So, I get p plus of s, and then when I differentiate e to the power of minus sx over c, I get s over c, and I will take this s over c outside the parenthesis. So, I get minus sx over c, or actually let us keep this negative sign inside. So, this should have been minus p plus times s e to the power of minus s x over c plus p negative, which depends on s, times e to the power of s x over c. So, this entire thing is in parenthesis. So, I have differentiated the equation 1 with respect to x, and this entire thing is multiplied by e to the power of s. So, that is the LHS of equation B, and this equals real of s u plus, which depends on s, e to the power of minus s x over c plus u minus s e to the power of s x e to the power of s t, because what I am doing here is I am differentiating equation A2 with respect to time. So, I am differentiating equation A1 with respect to x, which is this thing. So, I am connecting this with this, and I am putting it here. Okay. So, these things are connected, and similarly the left side, which is in purple, is connected to this negative, and I have to multiply this by density rho naught, and there is a negative sign here. So, I have to have a negative sign there. Okay. And this purple sign, this circle is coming from this equation. So, there. Okay. So, let us call this equation C. Now, equation C is basically a restatement of momentum equation. It is a restatement of momentum equation, which is this equation. And what is momentum equation? It is essentially a modified form or a particular version of Newton's second law. And Newton's second law is valid for all points, at all points of time and at all positions. So, what that means is that equation C has to be valid at all values of x, and it also has to be true for all values of time. And that is going to be possible only if this component equals the component on the right side related to minus s x over c, and this component times s over c is equal to the u negative term. Okay. So, we write these equivalencies. So, equation C is true only if following two relations hold. So, what are those two relations? So, first relation relates to P plus, and P plus is multiplied by S over C. So, S over C P plus S e to the power of minus S x over C equals minus S u plus of S e to the power of minus S x over C. So, these two guys cancel out, and of course, there has to be a density term rho naught. This is the density term. Okay. So, what we get is eventually u plus of S is equal to, so S also cancels out, and what else? And this is, there is a negative sign I missed here. So, these negative signs also go away. So, u plus of S is equal to P plus of S divided by rho naught C. So, this is D1. So, this is the first relation which has to hold true, and the second relation which has to hold true is S over C times P negative times e to the power of S x over C equals negative S rho naught u minus S e S x over C. Okay. So, once again S x over C gets cancelled out, so does S. So, what that gives me is u minus of S, which is the complex amplitude of the wave travelling in the reflected direction, is equal to negative of P minus of S by rho naught C d2. Now, what we do at this stage is we say that let Z naught, some constant Z naught or Z naught, and we define it such that it is rho naught times C. So, in that case, so thus, so if we look at equations D1 and D2, from D1 and D2 what we get is that u plus of S equals P plus of S by Z naught, and u minus of S equals P negative of S times Z naught, and there is a negative sign here. Okay. So, with this so this is equation E. So, now what I do is I combine equation E and our first equation, our equations for A1 and A2. So, once I do that, I get the equation for pressure and velocity, that P of x and t equals real of P plus of S E minus S x over C plus P minus of S E S x over C E S t, and u of x t I can express as real of, so u plus is nothing but P positive divided by Z naught and then u negative is minus of P negative, which depends on S, divided by Z naught times E S x over C, and this entire thing is multiplied by e to the power of S t. So, these are transmission line equations for pressure and velocity. I can also write this in matrix form as P of x t and U of x t, this is equal to real of P plus. So, I am going to omit the S term in bracket just for purposes of brevity, P negative P plus over Z naught and negative P minus over Z naught. So, this 2 by 2 matrix is multiplied by this vector E minus S x over C and E S x over C, and this entire thing is multiplied by a common term e to the power of S t. So, and this entire thing is closed in curly braces. So, this is the matrix form. And if we do not want to use the term real, then the left side can be expressed as complex pressure. So, complex pressure is capital P of x and t, and complex velocity is this thing. So, this is equal to P plus P minus P plus over Z naught minus P minus over Z naught E minus S x over C E S x over C times e to the power of S t. So, this is third form, okay. But essentially all of these forms depict the same reality. Now, some comments. We will look at some important comments. First thing, P plus S and P minus S are dependent on complex frequency which is S. So, they can change with complex frequency. Okay. So, for each frequency they have to be evaluated. Second thing is P plus of S and P minus of S are complex entities. Okay. They are complex entities in general. They can be real, but there is no reason why they have to be necessarily real. Third thing, Z naught is called characteristic impedance of medium and it is equal to rho naught C. So, what is rho naught? Rho naught is the density of the medium and C is the velocity of sound in the medium. So, this Z naught or Z naught, it does not depend on the boundary conditions, it only depends on the medium. If you change the medium, then Z naught changes, but the boundary conditions do not influence the value of Z naught. So, it does not depend on boundary conditions okay, or the length of the tube or whatever. Okay. It only depends on the nature of the medium. And the other thing is that it is a real quantity. it is not a complex number because rho naught is real and C is also real. So, it is a real quantity. The fourth thing is that this equation, so let us call this equation F1, F2, F3. So, there are two transmission line equations. But there are 4 unknowns. What are the 4 unknowns? When we look at the transmission line equation, what are the unknowns? P of x and t is unknown, u of x and t is unknown, p plus is unknown, p negative is unknown, z naught is known, okay, because we know the density and the velocity of sound. Also x is known. So, everything is known, but so other parameters are known, but these 4 are unknown parameters. So, what that means is, hence we need two additional conditions to solve for 4 unknowns. So, these conditions are gotten from 2 boundary conditions. So, if you have a closed tube or an open tube or a tube of finite length, it has 2 boundaries and you should know the conditions at both of these boundaries. Then you can solve for these 4 unknowns, otherwise you cannot solve for these 4 unknowns. So, that concludes our discussion for transmission line equations. What we have been able to do today is we have developed the relationship between pressure and velocity for these 2 transmission line equations, and using that relationship we have expressed transmission line equation in 3 forms, F1, F2 and F3. And then what we also see is that the transmission line equations by themselves will not be able to help you solve for the actual value of pressure and velocity at all the points in a one dimensional space. For that we need to know 2 extra conditions, and those 2 extra conditions typically come from the boundary conditions as applicable on a case to case basis. So, with that we conclude our discussion for today, and we will meet once again tomorrow, and we will continue this discussion on transmission line equations tomorrow as well. Thank you. Have a good night. Bye.